Okay, so mostly when we've been doing physics so far, it's been about linear stuff. So we've done things like we've had a coordinate system x and y, and we've said, you know, this is going to be my initial position, x0, this will be my final position, x. And the displacement between these two we call delta x, right? And if we measured a time, delta t, during that delta x, and we put delta x over delta t, what did we call that? We call that velocity, right? And if we measured our change in velocity over change in time, what did we call that? We called it acceleration, right? And we said these things are vectors, they have direction, they have a magnitude and all these things, and that's great. However, this only takes into account a very specific kind of motion, and it's not even the most common kind of motion. There's another kind of motion out there that we need to consider, and that is the motion where we start here, and we follow a path along a curve like that. What we call a curved motion. Then we have to consider some different things, because this isn't just point A to point B in a straight line anymore. It's along a curve, and if that curve is along a circle, we can start to talk about it in simple enough terms for the math for this class. So that's what we're going to do. We're going to assume that this point here is the same distance from here as this point. We'll say it's a distance r away from that point. And we're really just going to rotate from this point to this point along the edge of this circle that has a radius of r. And that means we're going to go through some angle of, we'll call it, I don't know, maybe theta. That's a good one, right? We'll call it delta theta. We'll start at this angle here, which we'll call theta naught, and we'll end at this bigger angle here, which we'll call theta final. And we'll say that delta theta now equals, guess what? Theta minus theta naught, right? Just like delta x was equal to x minus x naught. X final minus x position, right? So it's still a kind of movement, but it's just not in a straight line. It's along the edge of a circle.
It's like a trajectory?
No, a trajectory is different. A trajectory is not along the edge of a circle. A trajectory is along the edge of a parabola. Are you eating fried chicken for breakfast? Now we know you're from West Virginia. Fried chicken. I love fried chicken. All right. I'm not meaning to be, you know, West Virginianist or anything, but
Greatest state to you?
just reminds me of, I want to live in the South. It reminds me of the South. You gotta love it.
Brooke
Okay.
wishes she was from West Virginia.
Who was?
Brooke does. She wishes she was from West
I know. She told me that yesterday. Okay. So this right here is a different kind of motion. We're going to call it rotational motion, obviously. Makes sense, I guess. And we're going to use, instead of things like x, delta x, y, and delta y, we're going to use theta and delta theta. And we're even going to associate a rotational velocity with our rotational motion. We'll have, instead of a v for velocity, which is delta x over delta t, we're going to have something else. We're going to define a whole new set of things so that we can start to talk about this rotational motion. So let's go ahead and get started with it. So we start with our delta theta. Now delta theta is a rotation through an angle. It has nothing to do with a distance unless you know how far out your point is that you're talking about. So in other words, you have to know this radius before delta theta means anything with distance, because delta theta is just angle. If I'm talking about delta theta and I want to go 25 degrees in this room, from this end of the room, and I go 25 degrees, the distance on that end of the room is not very much, a few meters. But if I go 25 degrees and I'm talking about the distance to Lincoln, okay, That's hundreds of miles of distance that we sweep out when we do that angle, right? So it really depends on the distance r. And so that swept out arc, we call it an arc, is what we're going to call delta S. It's going to be the length along the edge of a circle. If we were using this CD as our circle, and we swept out this angle delta theta, then the arc would be this length of curved path along the edge of the CD. If you're not sure what a CD is, go look up the 90s, and you'll know what a CD is. Right? It's kind of like a DVD, but for music. So there's your delta S right there. And it turns out that delta S is directly related to delta theta by the radius. Well, it's inversely related to delta theta by the radius. So if you take delta S and divide it by the radius, you get the angle theta, but you don't get it in degrees. You get it in radians. So we have to become acquainted with what the heck is a radian. So anybody know what a radian is? What's a radian?
Another way of saying green.
I'm going to say no. Just because I want to say no. It's actually simpler than that. Radians is the definition of a circle. Plain and simple. What is the definition of a circle? The definition of a circle is this. Let's go back to my camera here really quick so I can show everybody. The definition of a circle is this. This distance here is what? 2 pi times r, right? That is that distance. We call it the circumference if we want to. But really, what it is it's the amount of distance around a circle of radius r right here, right? So if we say our radius is, say, 1, right? Then we have 2 pi of this distance. It's the definition. How many radians do we have going around a circle? In a full circle? 2 pi, right? 2 pi. So really, it's a very natural thing. This is one of the first natural fundamentals of the universe that was ever discovered. It was probably the first, actually. That was ever discovered. That is, if you have full angle going from one angle all the way around back to that angle, you get this 2 pi relationship, so we call them radians. And why do we like it? Because this equation that we were just talking about right here is this definition. This equation, theta angle this is radians equals distance around the circle divided by radius. So if you go the whole distance around the circle, what is this going to equal? This is going to equal 2 pi. But if you only go part of the way around the circle, it's going to be equal something different. If you go halfway around the circle, this is going to be pi, right? If you go a quarter, you can go more than once around it. You can make it 4 pi, or you can make it 7 pi, or you can make it 5 pi, or 2/3 pi, whatever, how much you go around a circle, you can make it equal to whatever, right? So if I ever ask you, pick a number between 1 and 10, you can almost be guaranteed I'm going to pick pi. Just in case you're wondering. So. Okay, so that is a definition, but we can use that definition to calculate the arc length for any angle. If the angle is, if you have 1 radian of angle, you put in 1 for delta theta, and that is going to equal the arc length over the radius of the circle. So you can calculate the arc length if you know the radius, or you can calculate the radius if you know the arc length, right? So this is just a simple definition of it. But it's one we need to know, because what this does is this takes us from an angular movement to a movement along a path, right? So it takes us from that angular to that arc path movement. So here they give you a little table of conversions. These are exact conversions. If you have exactly 30 degrees, it's exactly pi sixths. 60 pi thirds, so on and so forth. It's good to know these. If you don't know them, you know, look them up. But it's a nice table to have. But you can also calculate them. Right? How do you calculate them? Well, you use a conversion factor. And we know that there are 2 pi radians per full circle, and that is equal to 360 degrees per full circle, so there's your conversion factor. 360 over 2 pi, or 2 pi over 360. Some people like to do 180 over pi, or pi over 180. Either way it works out. It's about 57.3 degrees per radian. So each radian is like 2/3 of the, well, 1/3 of a circle. No, 1/6 of a circle. There we go. So each radian is about 1/6 of a circle. Did I just say that? Yeah? No. Each radian, yeah, 1/6 of a circle. Thank you. Got it. About. Now, if something is rotating at some rate of rotation, then we say that it has angular velocity. Angular velocity is denoted with this Greek letter omega. That's not a W. That is an omega. It is the last letter in the Greek alphabet. Right? Am I right? The last letter? Okay. So this is the last letter in the Greek alphabet. This is a lowercase omega. And it is not a W. So omega equals delta theta over delta t. Right? So you start at some angle, you end at some angle. Delta theta is the final angle minus the initial angle, just like we mentioned before. However, if you wanted to measure the speed along the edge of a circle in that rotation, the speed along the edge of that circle would be the change in the arc distance over time, wouldn't it? So that would be like here, I started here on the edge of the arc, and I ended here on the edge of the arc, and I measure that change in distance along the edge of the arc. It's not a displacement because it's not a straight line distance. So it's like starting here and ending here and traveling along this curved path. What is that distance divided by a time will give me a speed. And we still call it a v, even though it's a speed, not a velocity. We just don't give it a vector symbol, so it's not a vector, so it's a speed. And that speed is going to be delta s over delta t. Change in arc length over change in time. But delta s, if we go all the way back to here, delta s can be written as r times delta theta. Because if we rearrange this equation to solve for delta s, we get multiply by r on both sides, we get delta s equals r delta theta. So we can come back down here and we can rewrite the delta s as r delta theta. Then all of a sudden we have r times delta theta over delta t equals the speed along the edge of the circle, which is the same as r times omega. So now we have some equations to write down to remember. We have some things to write down to remember. First thing that we have to write down to remember is the relationship, which is this one. Well, it's this one right here, actually, but we'll rewrite it in general terms really quick here. Let me get my camera back up. Got to remember I'm recording. Where did it go? There it is. Okay. So let's talk about this. The radius of the circle. Let's draw a new circle. Where's that circle? I've lost all my erasers. Oh, here it is. Okay. So we have this one equation that says delta s over r equals delta theta, which means if I go from one angle, theta, to another angle, this is theta naught and this is theta here. If I go from one angle to another angle at a particular radius r, so this is r and this is r, then the distance traveled right here is delta s, right? And the relationship between the delta theta and the delta s is divide delta s by r and you'll get delta theta. So, if we rewrite this to calculate delta S, we get delta S equals R delta theta. In other words, to get the path length, we take the angle and multiply it by the radius. Okay? Radius times path length, radius times angle change gives us path length. But then, if we say that omega is delta theta over delta t, omega being angular velocity, or how fast we rotated from one angle to another angle, that's what omega is. And delta theta can be rewritten as delta S over delta R, or, delta theta can be rewritten as delta S over delta R. And so this is over delta T, also over delta T, right? Then we have this thing here, which is a speed. That's the thing they just told us about. So that's the speed along the edge of this path length. So we find out that omega equals the speed along the edge of the path. We'll call that the tangential velocity, V tangential. Right? Sorry, that's not delta S over delta R. It's delta S over delta T is the speed. And then we divide that by our R, our radius. And it's not delta R, it's just R. And then we have now, if we rearrange this equation, multiplying by R on both sides, we get the tangential velocity, or the velocity along the edge of the circle, equals R times omega. Notice the relationship here. The path length equals R times the angle. The speed along that path equals R times the angular speed. In other words, the angular stuff, when we multiply it by R, gives us the path stuff, the information along the path. We can get the distance along the path by multiplying by the angle by R. We can get the speed along the path, tangential velocity, times, if we multiply the radius times the angular velocity. So there's a pattern, and they'll show this in the book as well. So, but I want you to start noticing this pattern right away. So speed along the edge of the path, V, is equal to R times omega. Or omega equals V over R. You can write it either way, and you can use it either way. But let's look at an example of how these things are related. Here we have a car, the greatest car ever made.
Volkswagen Bug.
That's right. More of this car. This is the car that the most were made of. There's no car that's ever been made that's ever had more production models than the VW Beetle. And it's the longest lasting car on average than any car ever made. So it's the best car ever made, right? Anyway, first model in 1940, I want to say 41, 38, I don't know, a long time ago. Anyway, so this car is moving along. It has these wheels that are rotating. The wheels have a radius of R. The car is moving at a velocity v that is forward. Now you have to recognize, hopefully, that if the wheels of the car are not skidding, then the speed of the wheel, of the edge of the wheel, the speed of something that's traveling, like if you painted a white mark on the edge of the wheel, on the outside edge, the speed of that edge, of that rotating edge, the speed along that edge, would be equal to the speed of the car going forward, as long as the wheels aren't slipping, right? That's an important thing to realize, because we're going to use that a lot. If you have something moving forward on rolling wheels, then the rolling edge of the wheel speed is the same as the forward speed of the car, right? Hopefully that makes sense. It's not always obvious to people. But anyway, the point is this v forward of the car is equal to the v along the edge of the tire, which is our tangential velocity, which is equal to the radius of the wheel times the angular velocity. So if you know how much angle it's rotating through every second, and you know the radius of the wheel, and you multiply those two things together, you can get the speed of the car. And actually, that's how they calculate the speed of cars. Okay? That's how they calculate the speed of almost every car ever made, is by knowing the radius of the wheel and by measuring how fast it's rotating. Okay? Some newer cars use GPS, but almost nobody does that. It's very, very rare. Most cars use this. And this is the way that analog brakes work too, so you have to still have these meters inside your car. Anyway, point is they're saying that we want to calculate this angular velocity. We want to know what omega is when a 0.3 meter radius car tire is traveling at 15 meters per second. So this is the equation, omega equals v over r. We just rearrange it so that we're solving for the angular velocity. We have 15 meters per second is the speed along the edge of the tire, because that's the speed of the car, divided by 0.3 meters, 50 radians per second. Does that seem reasonable? 50 radians per second. How many radians are in a full circle? 2 times pi. So how many? About 6, right? So how many times is this car tire going around? How many rotations per second? If it's 50 radians every second, about 8 point something, yeah. Does that seem reasonable for a car moving about 30 miles an hour? Because 15 meters per second is about 30 miles an hour. Yeah, 10 times every time around for a car tire that's 0.3 meters, which isn't much. 0.3 meters is about a foot radius. So that's a pretty small tire, actually. Most cars are around 14, 15 inches. So that's a smaller tires have to go around faster to go normal speeds, right? So yeah, that's pretty reasonable. It makes sense. What if you had a car that had 1.2 meter radius? Holy crap. What kind of car has a 1.2 meter radius? A tractor or one of these big old... I saw a truck the other day that was on tires taller than my car, I swear. So, in fact, I saw a car on tires that big the other day too. Have you seen that car around town? It's like this old 70s or 80s like sedan, and somebody put it up on these huge tires. Crazy. But anyway, so if you're on 1.2 meter radius tires, that's over 6 feet in diameter, right? Then how many times is it going to go around? 2 times. It only has to rotate 2 times to go 30 miles per hour. That's pretty impressive. Does it surprise you that fast cars, that cars that are designed to go fast, have fairly large radius tires? I mean, if you go and compare, for example, your average, like my car, a Toyota Camry. I have a Toyota Camry that does go pretty fast for its size, for what it's meant for. It has 15-inch radius tires. But compare that to a Corvette. What does a Corvette have on the back wheels, the drive wheels? I think they're 18. I think they're, well, maybe not 18s. They're probably at least 17s. They're huge. They're almost 3 feet tall. They don't look that tall because the car is so small. But the car is so low to the ground, but they're huge because that car is meant to go 200 miles an hour. My car couldn't go 200 miles an hour off a cliff. So they want to be able to not turn the wheels too fast. Faster you turn the wheels, the harder it is to keep those wheels on the ground. The wheels wear out more, so on and so forth. And your engine has to turn faster too. So you'd prefer your engine not to have to turn too fast to go fast. Okay, let's look at the ladybug revolution. That looks like fun. Okay, so we're going to show the velocity vector. We're not going to show our acceleration vector yet. But the velocity vector, we're going to turn this thing. We're going to put a ruler on here. And we're going to turn this thing with an angular velocity. Right now it's at 0 degrees. 0 degrees is usually going to be on the x-axis, okay? And positive angle is usually going to be going in the counterclockwise direction. Negative angle will usually be going in the clockwise direction, okay? And we're going to start this thing with some angular velocity, so many degrees per second. I don't know why they've switched to degrees, but we're going to do it anyway. What is the velocity vector going to look like when we do this? Let's make this a quiz. We haven't done a quiz in a little while. No, let's not make this a quiz because not everybody's here. But let's make it an informal quiz. Which direction, we're not going to grade this quiz, but which direction is the velocity vector going to be pointing if we start this with a positive angular velocity, which means which way is it going to move? It's going to move counterclockwise, right? So the ladybug's going to start off going up. Which direction is the velocity vector going to be pointing when we start this? The velocity vector of the ladybug. It's going to be pointing straight up when we first start. But then what's going to happen to it? It's going to start to turn. And it's continually going to turn. And it's always going to be pointing perpendicular, right, to the radius from the center to the ladybug, right? It's always going to be perpendicular to that. Okay? So that's why we call it the tangent, because it's tangent to the path, the circular path of movement. So the velocity, the tangential velocity is always going to be tangential. So there's our velocity vector, right? My angular velocity right now is 134.65 degrees per second exactly. And it's going to go around and around and around. Looks like it's going to stop. No, it's not going to stop. It's just going to keep going. That's fine. What happens if I increase it? Well, the velocity vector gets longer, right? If I decrease it, the velocity vector gets shorter. That's fine. What if I go the opposite direction? Well, of course, it becomes a negative velocity and it just points the other way, but it's still tangent, right? Wow. That's a lot of stuff. We don't want to mess with that. All right. So, let's move on. Now let's talk about what kind of accelerations are happening here. Well, here is that same situation. Ladybug out here at point B to start with. But as it rotates, it gets to point C, and it has two different velocities, velocity 1 and velocity 2, two different directions. Is there an acceleration? The velocities are the same length, it's the same speed, but it's in different directions. Is there an acceleration? Yes. Because acceleration is defined by change in velocity, and change in velocity can either be change in speed, or change in direction, or both, right? It can be change in direction and change in speed. In this case, it's just a change in direction, and so what we do is we take the difference. Remember what we did when we took the difference of vectors? We put them tail to tail. This one is a little harder to remember because we only did it a couple times. We put them tail to tail, and then we drew a line from the first one, the head of the first vector, to the head of the second vector to get our difference in that vector. So if we put our velocity 1, which is pointing upward to the left, and velocity 2, which is mostly pointing to the left and less upward, put them tail to tail and then draw a change in velocity vector, it looks like this. And if we draw this vector, delta v, right between the two, right here, which way is it pointing? Straight towards, it's actually pointing from this edge, from here towards the center, and it's pointing straight towards the center of the circle. So, the acceleration that causes us to go in circles points which direction? Towards the middle of the circle that we're on, right? We call it a centripetal, which literally means pointing towards the center. Center pointing, centripetal acceleration. So the acceleration that causes velocities to change constantly so that we always stay on the edge of a circle is called a centripetal acceleration. And this is this is how we derive the equation for it. We have a change in velocity, a change in velocity, change in v over change in time. We get this equation that looks like this, change in v, right? If we divide it by the v, we actually are going to get delta S over R. Because delta V divided by V is delta S. And then we have an R in there as well. So, you can also, the way that they explain it is they're similar triangles. Here's the similar triangle with the V's and the delta V. Here's the similar triangle with S and R, right? So the delta S and the delta V are the similar sides, and the R's are the similar sides to the V's. So you can make this same equation that way as well. But in the end, you solve this equation for delta V to get V over R times delta S. And then, so V and delta V are different things. Remember that V is the speed along the edge of the circle. I prefer that they put a T here, but they don't. V is the speed along the edge of the circle. Delta V is this vector difference. So it's this thing right here, whereas V is the speed along the edge of the circle. So now we have delta V, which is the vector difference, equals V over R times delta S. And if we divide both of these sides by delta T, then delta V over delta T is acceleration, right? That's an acceleration. And that equals, when we divide this side by delta T, that equals V squared over R when we do all this mess over here. We get a V over R times delta S over delta T, and delta S over delta T is another V, so it becomes V squared over R. You don't need to remember all this. This is the derivation of the formula, but this formula you should remember. The centripetal acceleration of an object moving this has to be moving at a constant speed along the edge of the circle, constant speed of v, along the edge of a circle with radius r is v squared over r, and that tells you how much acceleration is required to keep it going along the edge of that circle. This tells you how much acceleration is required to keep the Earth going around the sun. Let's calculate that. Okay, so how fast is the Earth going around the sun? So the speed of the Earth, Earth is moving about the sun, circular, it covers the route at a speed of 30 kilometers per second. So that's 30,000 meters per second, right? And what's the radius, so the distance between the Earth and the sun? So let's write this down. 30,000, so 30,000 meters per second is our speed, and our radius is 93 million miles times 1 point, whatever. Earth from sun. Distance from the Earth to the sun is, I don't want that one, I want the in meters. So it's 149.6 billion meters. So 149.6 times 10 to the 9 meters, right? And this is 3 times 10 to the 4 meters per second, right? And what are we going to do? We take the speed squared, so our acceleration, centrifugal acceleration equals v squared over r, or speed squared over r. So it's 3 times 10 to the 4th meters per second squared over 149.6 times 10 to the 9th meters. And 3 times 10 to the 4th squared is like 9 times 10 to the 8th, right? Meters squared per second squared, divided by 149 times 10 to the 9th. The 10 to the 8th and the 10 to the 9th cancel out to equal times 10 on the bottom, just times 10 on the bottom. So we get a 9 over, and this is meters down here, the meters squared divided by meters leaves us with meters per second squared. So it's going to be 9 over 149 plus a 0 meters per second squared. Not very much acceleration, is it? 9 thousandths. So this is about one. This is about a half a meter per second, half a hundredth of a meter per second of acceleration. That's how fast we move towards the sun every second to stay in our orbit. Every second we move about a half meter towards the sun. Almost half a meter towards the sun. Not very much. Actually, it's not even half a meter. Almost a tenth of a hundredth of a meter. Almost a thousandth of a meter. Not very much. Almost a hundredth of a meter? I don't know. Whatever. Not very much. Tells you how weak gravity actually is. But it reaches a long way. So let's talk about the acceleration of a car moving around a curve compared to the gravitational acceleration we feel from gravity on the surface of the Earth. So centripetal acceleration of a car moving following a curve at a radius of 500 meters, so there's your radius, at a speed of 25 meters per second along the edge of the circle. Compare the acceleration with that due to gravity for this fairly gentle curve taken at highway speed. Okay? So we have a speed, we have a radius. We take the speed, we square it, we divide it by the radius. It's pretty simple, right? Square 25 meters per second, it has to be in meters per second. So we square that, divide it by 500 meters, and we get about 1.25 meters per second squared. And what's the acceleration that we feel due to gravity? What acceleration do we feel from gravity? 9.8 meters per second, right? That's how much, when we're on the edge of the Earth, we are moving towards the center of the Earth all the time at 9.8 meters per second squared to keep us on the surface of this Earth. If we didn't feel that, we would go flying off the edge of the Earth. We would start rising off at 10 meters per second, right? So that's how much we're being pulled towards the center to keep us in orbit with the Earth. We're all in orbit with the Earth. Isn't that nice? We just happen to be in orbit on the Earth. But going around a curve like this, you don't feel nearly that much gravity. And you shouldn't. Because if you did, if I was turning a corner on freeways and I felt the same amount of acceleration as I did with gravity, how hard would I be pushed around in the car? How hard would the car push against me is a better question. Well, it would push against me with my weight. And I weigh 200 pounds. Do you feel 200 pounds of pushing on your seatbelt when you turn a corner? No. And thank goodness. That would hurt, right? This is 1.25 meters per second, which is, not even a sixth of what I weigh, which is nice. And this is why people in race cars have a lot more belts on them, because they feel a lot more of this force going around corners at 200 miles an hour. At 200 miles an hour, you start to feel your own weight going around the corners. And you want to spread that weight out over lots of belts instead of just one belt. Right? Now here's a question for you. When you're going around that corner in your car, what is it that keeps you going in that circle? If you're in a car, what is the thing that keeps you personally in that car going around the circle? If there's an acceleration, doesn't there have to be a force? So what is the force that's causing the acceleration as you go around the circle? What keeps you personally, not the car, you personally going around that circle? What's that? I can't hear what you're saying.
Gravitation.
Gravitation? No, it's not gravity. Well, gravity plays a little role in it, but it's not directly
The
playing.
fact you're attached to the car.
Okay, so what's attaching us to the car? The seat belt. So as we turn the corner, we feel like we're getting pushed outward. If I'm going this way, I feel like I'm getting pushed outward. But what's really happening? What's really happening is the car, I'm trying to go straight, because if the car wasn't there, I would go straight, wouldn't I? If I was in a Jeep without any doors and really oily seats and no seatbelt on, and I turn a corner real fast, I go sliding off the seat out the door straight. Well, the car turned, right? But if I have my seatbelt on and the seat's not oily and I'm holding on to things, then as I turn, what happens is the car turns in front of me and I run into it. I run into the seatbelt, or I run into the door, or I run into the steering wheel that I'm holding onto, and it pushes me back into the right position, and I run into it again, it pushes me back. And so it's all these different things inside the car. We often think of the car pushing on us, we think we're being pushed into the car, but really the car is turning into us and it's pushing us back into the circle, right? So just like we call this centripetal acceleration, that force of the thing pushing us back into the circle all the time is the centripetal force. We'll learn more about that later. But for now, we'll just start with centripetal acceleration. Now we're going to do how big is the centripetal acceleration in an ultracentrifuge. So a centrifuge is one of these devices that you put little bottles of things in, bottles of liquid in that have different stuff in them, non-heterogeneous solutions in, so that you can separate the stuff that has a higher density from a lower density. You spin it around going really, really fast. And the centripetal acceleration, which is pointing towards the center of the centrifuge, or towards the center of the rotational motion, then it has a higher, that force that is causing that centripetal acceleration creates a larger force on the smaller objects, right? Because it's the same acceleration for every object, but the smaller, or the less dense objects, they feel more of a force from that same acceleration. In other words. So they actually end up, the stuff that's heavier ends up further out towards the edge because it doesn't get pushed as much, and the stuff that's lighter gets, well, you could think of it either way, but anyway, the point being is that it separates the higher mass stuff out here, or higher density stuff out here, and lower density stuff out here. It's a way of getting your precipitate out of your solution, right? So we want to know what is the centripetal acceleration at a point 7.5 centimeters from the axis of the ultracentrifuge, spinning at 7.5 times 10 to the fourth revolutions per minute. Now, notice they haven't given us the spinning rotation. They haven't given us the rotational velocity in the correct units, have they? They've given it to us in revolutions per minute, which is RPM. And RPM is not radians per second. We need to make a conversion. So what is the conversion from RPM to radians per second? Well, how many radians are there per revolution? 2 pi radians. How many minutes are there per second? There's 1 minute for every 60 seconds. So we have to set up this conversion. It ends up being 2 pi divided by 60 to convert RPM to radians per second. So we do that and we get 7,854 radians per second, which corresponds to 75,000 revolutions per minute. And then we plug that in. Now that's our omega. We can plug that into our equation. Now remember, we used the last time, we used the equation where it was velocity squared over r. But there's another version of it because of the relationship between the velocity and the omega. Remember that velocity equals r times omega. So if we plug in r times omega into this equation, we get centripetal acceleration equals r times omega squared. So now we have two equations for the centripetal acceleration. We've got an omega of 7,854 radians per second. We square that and multiply by the radius, which was given to us as some number of centimeters, which we convert to meters. So 0.075 meters. Multiply that in here. We get 4.63 times 10 to the 6 meters per second squared. Now, how is that compared to gravity? Holy crap. That's a lot of acceleration. Much higher than a human being can withstand. I think the highest ever survived is like, I don't know, 100 times gravity or something like that was survived barely with some damage. But this is, a lot bigger. 4.72 times 10 to the 5th times gravity. So we could never survive that kind of acceleration. Okay. Let's watch another ladybug show here. So here's our ladybug going in a circle. Constant velocity, so the constant speed, but changing velocity. The velocity arrow is changing direction, but the magnitude of the green arrow is always the same length. So it's at a constant speed along the edge of the circle, and the acceleration is always pointing towards the center of the circle. So the acceleration is always changing as well. Its direction, but it's keeping its magnitude as well, right? Can I change its, whoa. It went back to its original spot. Doesn't like where I put it. I wanted to move it. I want to move you. Woo! Okay. All right, enough of that. Now we talk about centripetal force. If there is an acceleration, there is always a force. And the centripetal force is the name we're going to give to the force that causes things to move in circular motion. And just like with all forces, force is going to equal mass times acceleration. Centripetal force will equal the mass that is being accelerated times the centripetal acceleration. Simple enough. It's no different than before, except that we have all these equations for centripetal acceleration. So now we have centripetal force can equal mass times velocity squared, or speed squared along the edge of the circle, divided by the radius of the circle. Or centripetal force can equal mass times the radius of the circle times the omega, or the angular velocity squared. So if we know either the speed along the edge of the circle and the radius, or the angular velocity in the radius, then we can calculate centripetal force. But another thing that's really useful here is we can actually calculate the radius if we know the force, the mass, and the speed. Or the radius, we can calculate the radius if we know the angular speed, the force, and the mass. And that is used a lot in different situations, particularly in things like scientific instruments. It's used quite a bit. So how is it used? Well, according to this equation right here, as the force gets bigger, what happens to the radius? If the force gets bigger, since it's in the denominator, what happens to something that gets bigger in the denominator? It gets smaller, right? So if you have a bigger centripetal force, you're going to have a smaller radius to your rotation, right? If you have a smaller centripetal force, you can have a bigger radius to your motion. And so this can be used to measure forces. It's used a lot to measure, for example, magnetic forces or other kinds of forces. But in this case, we're just going to use the previous equation to calculate the centripetal force needed to turn a car. We'll start off with this one, then we'll go to something a little more advanced. So we have a car right here that's going, it's a 900 kilogram car. It's going 25 meters per second on a 500 meter radius curve. We want to know how much force is needed to turn this car. Why would that be important? Who would want to know this information?
Race car driver, car company.
Race car drivers actually give a flying fig. The tire company cares, right?
Yeah, tire.
The race car driver just buys the tire. Well, he doesn't even buy the tire, he just drives the car. But he might want to know how fast he can go around that corner, right? So he might switch this equation around and say, what's the speed I can go around this corner? So if he solves for V, and he plugs in the radius of the curve, and he plugs in the force that the tire company tells him he's going to get out of those tires, then he can calculate the speed going around. That's what he might want.
And the first thing he's going to say is, I can do faster than that.
That's right, and then he's going to screw up. Actually, race car drivers are very good at driving around corners at great speed. Race car drivers that are successful, because if you ask a race car driver what wins a race, they'll tell you two things: turning and tires, every time. Because those are the things that get you through a race. Changing tires takes more time than anything else, and turning corners takes more time than anything else. So if you go around them at too fast or too slow a speed, you lose. Too slow, you lose because of time. Too fast, you lose because of tires. It's the end of the story. That's all there is to racing. Applying that is difficult, but that's all there is to racing. So, and it's different for every car and for every track, and for every condition, temperature, rainfall, everything else. You know, there's so many different factors. So it's all about science, and every single racing team has an engineer on it, and they know these things, and that's what the engineer is there for, is to calculate these things. So anyway, the point being is that this equation is very useful. In this case, we're going to use it to calculate, we're going to be the tire company. We're going to calculate what force we're going to need to get these tires. And the force is going to be, we're going to, you know, the tire company is going to take this information, they're going to design a tire with the right width, with the right kind of rubber, with the right kind of tread for that tire to put this kind of force down, right? So we need to know the mass of the car, 900 kilograms, the speed squared around the turn, the radius of the turn, and then we're going to get 1125 newtons. If you're the tire company, you're also going to need to know the surface and the kind of rubber you're going to use, because that's going to determine your coefficient of friction, right? Because you'll need to know the coefficient of friction to calculate this, you know, all this other information that's going to come. But anyway, they're going to do that right in the next thing, actually. So right here, they're going to calculate they're going to calculate what they're going to assuming an unbanked curve, find the minimum step, so we're going to find the static coefficient. Why is it a static coefficient of friction? Why isn't the other one?
The tire's not sliding on it. The tire's loose.
Because the tire's rolling along the surface, right? So it's if it's skidding, it's a whole different thing, but we don't want to skid. We want to roll around the corner, right? And even if it wasn't rolling, if it skids one way and not another way, it's still static coefficient, right? Because it depends on which way you're moving. But since this is centripetal force, the force is always perpendicular to the movement. So even if you're speeding forward, the static force is still sideways, right? So in this case, it's always static, unless you slide sideways. But anyway, so we take the answer from here, and we plug it in right here to get this centripetal force is going to be our frictional force. Friction is going to be our centripetal force, so it's going to be μs times the normal force. The normal force, since it's not on a banked curve, since it's flat, it's just the mass times gravity, right? Banked curve will change everything. Your frictional force is going to have to be higher or lower if you're on a banked curve? Lower, right? You don't have to have as much friction when you bank the turns. That's the reason they bank them, so that you can go faster without having to have that friction. Now, around Nebraska, you don't see banked curves very much. But in California, where you have, 8-lane highways and they're going 70 miles an hour through these hills and mountains, you see this freeway that's 150 yards across, and the whole thing is turned at 12 degrees or something. It's kind of impressive. And people are just zipping through, no problem. So that ends up being μs times mass times gravity, and we want to solve for the μs using the numbers that we have. So when we do that, μs ends up equaling the velocity squared divided by the radius of the curve times gravity. Notice that the mass is on both sides of the equations. It's in the centripetal force and it's in the static friction force. Is that a good thing? Is it good that the mass is on the way? Are we glad that the mass is not in this equation? What would happen if this equation had mass in it and you were trying to design a highway that worked for every kind of car? It wouldn't work because you have to design a different highway for every car, right? That would really suck. I'm driving a different car today, I'm going to have to take a different highway, right? That's not going to work. You can't do that. And so it's really nice that it drops out. The only thing that really matters is the speed of the car and the radius of the turn. Nothing else matters unless you're on a different planet where G might change, right? So this is really great for highway makers. All they have to do is know the speed that you're going to turn these turns at and the radius that you're going to turn them at, and they can design the road properly. And if you're on a flat freeway that is high speed and has fairly sharp turns in it, they will design those turns differently. So the material on the road will actually be different in the turns. You may have noticed that in certain parts of certain freeways, it's a little rougher. The road's a little rougher or a little smoother in certain spots, and that's not on purpose. sometimes the rougher is the higher coefficient of friction, sometimes the smoother is. It depends on the material. Sometimes some materials are higher coefficient when they're smoother, some the other way around, but usually it's smoother. Not always, but. Anyway, you plug in your numbers, you can get a coefficient of static friction for that turn of 0.13. And here is the picture of what that looks like. As you're turning to the left, right, the coefficient of friction that's turning you to the left is also pointing to the left, right? You might think the friction is this way, but it's not. The car wants to go out this way, right? So the friction is back towards the middle of the, so it's out from the outside of the circle in on the outside of the car wheels. And that friction is the pavement pushing on your tires that way. Now in a banked curve, it's a whole different ball of wax, right? On a banked curve, your force, your force from gravity, your weight force is down this way, right? But your normal force is this way, and the normal force is the thing that's used to calculate friction, right? But where's your centripetal force? Where's the force that keeps you towards the center of the circle? It's still pointing towards the center of the circle. And the good thing is that part of your normal force is pushing you towards the center of the circle. So the normal force has a coefficient in the inward direction right here. So the normal force from the ground does part of the turning for you. So it doesn't have to all be done with friction. The frictional force is still pointing this way. Your car wants to slide up this way, so it points parallel to the surface this way. And only part of it is used to turn you towards the center of the circle. So you have two forces that contribute to your centripetal force. You have your normal force contributes to your centripetal force, and the part of the friction force contributes to this, but not all of the friction force. So it's an advantage because you don't have to have as much friction force. The normal force does part of the job. So, what is the ideal speed to take a steeply banked tight curve? How do you do that? Well, you can do that. You can calculate that by using, let's see, they work it out right here. We start out with this right here on the left side is this part of the normal force. It's the centripetal force that comes from the normal force, right? So this is our centripetal force right here, n times sine theta, the normal force times the sine of theta. That has to equal the centripetal force, which is m times v squared over r. Then we can actually, in the other direction, the n cosine theta, which is this one, that's this part of the normal force, has to be equal to the weight, has to cancel out with the weight. So this one is a centripetal force, this one has to cancel out with the weight. So we get this equation here. Then if we combine these two equations by dividing them, divide this equation by this equation, you get mg times sine theta over cosine theta equals mv squared over r. Cancel out the m's, right? Divide both sides by g, and we get tangent of theta equals v squared over r times g. So this equation has a lot of things in it. It has the angle of the angle of the bank, has the speed, the ideal speed for going around it, and the radius. So if you know any two of those things, you can calculate the third one for an ideal turn, right? So in this one, they want to know what is the speed. So we take this equation, we solve it for v, we get that, and we plug in all the numbers, 45.8 meters per second. So there you go. Now you can join a Formula One racing team and you can calculate the speed going around a turn, as long as you know all that other stuff. Now this is ideal. What does this mean? What does ideal mean in this case? This means that the friction is not going to have to do any work for you. This means that the curve is banked perfectly for the car to turn at that perfect speed. And that's exactly what they want to happen in a race. but it's never exactly what happens. When that doesn't happen exactly, you slide a little bit up the curve, or you slide a little bit down the curve. And when you slide up and down the curve, you ruin your tires more quickly. Just rolling the tires ruins the tires because you have what we call rolling resistance, which is essentially just heat that essentially evaporates your tires. That's why tires go bad mostly, is because they just evaporate from heat. But if you slide sideways, you get more. You get twice as much of that because the static coefficient of friction is higher than the kinetic one. And so you get a much, you have to overcome that static coefficient of friction. When you slide, you get a lot more energy loss and a lot more tire damage. So the ideal thing is to not have any friction. That's why there's no friction in this equation. If you were sliding up the curve or sliding down the curve, then you would have to add in a friction thing here, and it would increase the necessary, increase the amount of centripetal force you would need to keep it on the track. So this is ideal with no friction. This also explains why speeds in Nebraska have gone up to 75 miles an hour on highways, because they don't have banked curves. In California, they're still 55 or even 50. On some of these banked curves, it's as low as 50 because they were designed for that, and it doesn't change it. Having airbags doesn't change that. If you go faster on these curves, you will wear out your tires, you'll slide up and slide down the banks. They're designed for specific speeds at specific radiuses. So they haven't changed those speeds at all over the years. Also, there's just too many cars to go that fast. I want to look and see if there's a picture. Banked freeway Oakland. That's where they mostly are. See if they show a nice picture of the banked freeways going through Oakland. No, those are all the bridges. Those are all in flat places. There's one. There's a nice picture of the banked roads going through the hills near Oakland. Not the best one I've ever seen, but it's decent. Oh, how cute. Otters.
River otters back.
There are restaurants on the bay in San Francisco where you can actually eat your dinner and watch otters eating their dinner from the windows. It's kind of funny. And your fish is not much less fresh than theirs, actually. All right, moving on. What time is it? Time, okay. Yeah, I like it. Okay, now, we're going to talk about fake forces now. Talked about this a little bit already. When you're in a car and you're turning right, you feel like you're getting pushed to the left. But what's really happening is the car is turning into you and it's pushing you to the right, right? So that's the real force is what we call the centripetal force, and that's the car pushing you towards the center of the circle. But the one that we think we feel when we're in a car that makes us feel like we're getting pushed into the door is what we call the centrifugal force. Centrifugal. And that's often called a fictitious force, or they also call them pseudo forces. So in our frame of reference in the car, it feels like a real force. But guess what? In everything we do, we're in a frame of reference that makes us feel like our forces are real. Everything on Earth is within a rotating, orbiting system that is completely not true, right? There's no such thing as a frame of reference that is completely stationary. Everything is moving all the time around us. And so it's not really all that brilliant or bright to say, well, right here, this is a real force, so you're not feeling a real force because you're inside the car. None of us are feeling real forces. So we need to recognize that. We need to recognize that the point of your frame of reference is important to the observer. And to the observer, that force is real. And so we need to be able to account for it. Now, the physics of doing that, the mathematics, is way beyond this class. That's something that we don't do in physics until at least junior, senior year of the university, or maybe even graduate school. We don't really get into it until graduate school work. because it's extremely difficult stuff. But it can be done, and physics still works in those frames of reference. It just gets a little funky. But we call these forces fictitious or pseudo forces. Can you think of any other fictitious or pseudo forces you've experienced besides this one that you feel when you're turning a corner? Have any of you ever been in a rotating room at a carnival? Right? You ever tried to throw anything in that room? They always tell you not to, but you got to do it. If you don't do it, you're really missing out. It's really cool. You get in one of those rotating rooms and sneak a ball in and try to throw the ball to the other side of the room. What's going to happen? If the room is rotating around you to the right, as the other side is moving to your right, the ball is going to look like it does what? It's going to look like it moves to the left, right? And that's a fictitious force. It's totally awesome. I want to make a rotating room for this campus just to do this. Haven't figured out how to do it in a way that they'd let me do it. But we had one of these rotating rooms at the university I went to where you actually got in, you walked in this door, and you got in, you sat down at a table, and there was all these things on the table you could play with, and they started up this room rotating, and would go, and you didn't even know. I mean, you feel a little jolt at the beginning, and you could hear it, but you couldn't feel anything really, because you can't see anything. So you're just in a room with people, and you pick up a ball and try to toss it to the guy across from you, and he goes winging off to another direction, hit somebody in the nose, or you take a squirt gun and try to squirt this person, and it squirts this person, and it's totally awesome. It's just, and we call this the Coriolis force. Okay, the Coriolis force is a force caused by trying to do something across the motion of rotation. Okay, whereas the centrifugal force was something on the edge of that rotation. This is trying to go across that rotation. Now, we've had a lot of events in the world recently that have to do with this force. What are they? Hurricanes. Hurricanes are caused by the Coriolis force. They're caused by winds that are moving across a rotating platform. And as they move across this rotating platform, they look like they turn. Well, they really do turn according to our frame of reference, right? If you were out in space watching this thing happen from out in space, and not even noticing there was an Earth underneath it, you might just say, oh, there's just a storm front going across space. But as the Earth rotates under it, it makes it this big rotational thing and causes damage. Major damage. Loss of life, right? So you get these huge storms that cause serious problems, and this is what it looks like. Normally, you'd have these winds coming into this low pressure region. They would just come in and they would just hit together, and they would just crash, and that'd be done, it'd be over. But as the Earth rotates, they start to rotate around each other around that low pressure region, and that low pressure region becomes a huge wind problem, huge windstorm. Now, here near the United States, we call them hurricanes. Anybody know what they call them in Australia or India? In India, they call them cyclones. In Australia, they call them willy willies. Just in case you're wondering. So, they're having a willy willy. Another one that we see every day: toilets and drains. So toilets the rotation of water in a toilet is actually affected by this. If you do not design the toilet or design the drain to rotate in a particular direction, it will most likely rotate in the direction caused by the Coriolis force. Okay? You can design toilets to go the other way, but why would you? They would be less efficient. They would be fighting this force, so they're designed to go that way. Essentially, toilets are designed to work in the northern hemisphere or the southern hemisphere. Okay, and if they're designed for the southern hemisphere, they're more efficient for the southern hemisphere, and vice versa. So it's kind of funny. Coriolis force. There's one more. There's the centrifugal force and the Coriolis force, and then there's one called the I can't remember what it's called. But that one is a little more complicated. I don't think they even mention it here. Coriolis, yeah, just the Coriolis force. The other one's called the, I can't remember. Oh well, I think it also starts with a C. I remember something about it. Okay, moving on to the last two sections, and then we'll turn you loose on your homework for the rest of the week. Newton's universal law of gravitation. Most people say Newton's law of gravitation is force equals m times g. Well, it's not. Newton discovered the gravitational law between all things, not just between us and the Earth. Force equals m times g is just the law for us near the surface of the Earth and the Earth. M times g doesn't even work if you're not very close to the Earth. If you're far away from the Earth, it doesn't work anymore. It only works when you're very close to the surface of the Earth because it depends on the distance between the two objects. And the distance between us and the Earth is always the same when we're on the surface of the Earth. What is it? What's the difference? What's the distance between us and the Earth when we're on the surface of the Earth? If it was 0, the force would be funny. It's not 0. It's actually, there is some distance between us and what part of the Earth? The center of the Earth. So it's always between the center of the objects. So what's the distance between us and the center of the Earth when we're on the surface of the Earth? The radius of the Earth, right? So the radius is the thing that is the distance between us and the center of the Earth. What Newton discovered was this law right here. Force is equal to the two masses divided by the distance squared between those two masses, which we call r squared. But it has to be multiplied by a constant for this to actually be an equation, and that constant is the universal gravitational constant, g, which is 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared. What is that number? I'll tell you what that number is. Newton was doing a bunch of experiments, and he discovered that if you measured the mass of the two objects and the distance between them, that the force was always proportional to the mass times the mass divided by the distance squared. Always proportional. And it was always the same amount of proportion. It was always proportional to this every time. And it was not equal to it, but if you multiplied by this number that he found out, that he discovered, 6.66 times 10 to the minus 11, it was always equal. So he said, that must be an important number. I'm going to name it after myself and be famous. This is what physicists do because they don't get paid very much. So they name things after themselves and they become famous. So he just plugged, this is a fudge factor we call it, right? This is the number that makes this equation true every time. But because it's the same number every time, it's important. We call it a constant, right? Because it's the same number every time. It was really that simple. He had a proportionality thing. He turned it into an equation by plugging in the number that made it an equation. He just figured out it's always off by this amount every time, so I'm just going to multiply by that amount and call it good. Right? So if you ever find an equation that's always the same every time, but you have to multiply by some number to make it good, tell me about it, and I'll share a Nobel Prize with you. Okay? Anyway, that's how you become famous in physics. So how is this related to force equals m times g? Well, the force is the same. It's just the equation on the other side that's different. So if m times g and g times mm over r squared is the same, then what is different? Well, the thing that's the same on both sides is the mass of the person or the mass of the object that's on the Earth. And then the big M is going to be the mass of the Earth. And then we have big G over here and we have r squared over here. Well, let's calculate little g and see what we get from this. If we divide both sides by m, we get this equation. Big G times the mass of the Earth divided by radius squared. We plug all those numbers in, looking them up, and we get 9.8 meters per second squared for G. And that's what we told you what G was all along anyway. Right? So G actually comes from this equation by plugging in the mass of the Earth, the radius of the Earth squared, and the gravitational constant that Newton figured out, and you get G. Hooray.
It is third, fourth, centrifugal.
I'm sorry? Is the
Third force.
is the gravitational force centrifugal?
No. I was thinking about previously because I didn't remember it there. Centripetal, centrifugal.
Yes. So centripetal force is the force that points in. Centrifugal force is the fake one that points out. Does that make sense?
Centripetal within.
Centripetal is the real force that keeps you going in a circle. Centrifugal is the force that you feel when you're in the car that makes you push against the door, right? Pushes you against the door. That's the fake force. So let's calculate Earth's gravitational force on the moon. So gravitational forces are always pulling forces, so Earth's force on the moon is pulling the moon towards the Earth. Okay? And we want to calculate that. We need to know the distance between the moon and the Earth. We'll go look that up. Turns out it's about 3.84 times 10 to the 8 meters. Right? That's what it says. And the mass of the Earth is the same as it was before, 5.98 times 10 to the 24 kilograms. And we want to find, let's see, part A is find the acceleration at the distance of the moon. So the acceleration from Earth's gravity at the distance of the moon is just the g at that point. They're calling it g. I don't like to call it g, but they are calling it g anyway. So they're just dividing out the mass of the moon on both sides of the equation. And they get this 5.98 times 10 to the 24 divided by the radius squared up there. And it gives you 2.7 times 10 to the minus 3 meters per second squared. Not very much acceleration to feel that far away from the Earth, right? Millimeters per second squared. And that really tells you how much the moon is moving towards the Earth every second. The moon moves towards the Earth every second 2 millimeters, 2.7 millimeters. But it also moves away from the Earth about that much at the same time. So, because it's trying to get away all the time. So the Earth has to pull it back 2.7 millimeters every second to keep it in orbit. And then for part B, they want to calculate the centripetal acceleration needed to keep the moon in its orbit compared with the value of acceleration in Earth's gravity you've just found. So we calculate that using the v squared over r, and we get 2.72 times 10 to the minus 3 meters per second squared. Same number, approximately. Right? So we calculate it two different ways, and we get a value that's less than 1% off, which is not bad. Why is there a difference? Well, because the moon doesn't travel in a perfect circle around it. The Earth does it. Because the moon also pulls on the Earth. So while the Earth is pulling on the moon's pulling on the Earth, and the sun is pulling on the Earth, and the sun's pulling on the moon, and everything else is pulling on it, so nothing is exact. So the Earth's orbit starts to wiggle as it goes around the sun. The moon's orbit wiggles as it goes around the Earth. The Earth wiggles back and forth. Everything wiggles around all the time. We call these tidal factors. Here's another tidal factor you're more used to seeing on Earth if you're near the ocean or near a very large body of water. Large lakes you'll also experience this. High tide and low tide, right? When the moon is on the same side of the Earth as the sun is, or on the opposite side of the Earth as the sun is, you get high tides lining up with the Earth and the moon, or the sun and the moon. So if the sun was over here, moon's over here, or the sun and the moon are both over here, you get high tide. Why do you get high tide? Well, because if the sun's over here, you're getting high gravity pulling on the water, and the water can flow. So the water moves to those sides of the Earth. But if the sun and the moon are both on the same side, then you get extra high gravity on one side and low gravity on the other side. So water hangs out, stays there, and then you get the water coming over here. But wherever you don't have the sun and the moon, you get low tide. But every once in a while, you get the moon rotating around to this side and the sun staying on this side. So it kind of evens things out. Things start to, you get the sun pulling the waters this way, the moon pulling the water this way, and you get what they call neap tides. Well, here they show it. Here's a neap tide with the moon on one side and the sun. So whenever this happens, you're going to see like a half moon, right? You see half moons because the sun is only lighting up half the moon for somebody that's on this, somebody that's, well, might even not even see the moon during that time of day. But it's either like part of a moon or a quarter moon or half moon or something like that.
So spring
Or even a new moon. New moon. What's that?
So spring tide occurs during the new moon?
Yeah, spring tide occurs when you have no moon in the sky, even though it's in the sky, the new moon, right? So you can't see the moon even though it's up in the sky at night. Spring tides happen. Spring tides are when the moon is either aligned on one side or the other or on the same side, right? So that's when you have that new moon. Or a lunar eclipse. Also, right? Which is this here is a lunar eclipse. This is a new moon, right? In the sky. This would be a lunar eclipse. If this was slightly this way, then it would be a full moon. So it can happen during a full moon, lunar eclipse, or a new moon. So it can happen all kinds of times. But anyway. Here's the best thing to talk about when you're talking about gravity, right? When you're talking about gravity, you got to talk about black holes. So stars sometimes get so big that they cannot support their own mass, that the density of the star doesn't have enough strength to hold the star apart, to keep it that big. And when that happens, that the star can sometimes collapse. And when it collapses, a lot of interesting things happen to it quantum mechanically at an atomic and subatomic level. But what sometimes happens, and it turns out this happens often, we're discovering, is that all the protons and the electrons decay, or they change into neutrons. When there's a bunch of protons in a star, the star is not very dense, because protons don't like to be near each other, so they push each other away from each other all the time. But eventually that pushing away just can't happen anymore. Collapses, all the protons and electrons in the star become neutrons. And the details about that aren't important. We'll learn more about that next semester. But when you have just neutrons, neutrons don't push away from each other at all. Neutrons can be as close to each other as possible in the universe. So it becomes extremely small and extremely dense. And if that star was big enough to start with, if it was huge to start with and had a lot of mass in it, then the density of that neutron star can be so dense that it will start to suck in everything around it because of gravity. The gravity will become almost infinite when you're close to the star. And so things that are around it, other stars, planets, it just starts sucking things in. And it can eventually become so dense that even the light around it gets sucked in. Because light can be sucked in by gravity, it turns out. And this is all Einstein's stuff. So you get this phenomenon that we call curved space, where space is literally being bent by this gravitational well. And so they call it a black hole because the only thing you could see if you looked at a black hole was blackness, because all the light that's near it gets sucked into it. Anything that's got light coming away from it that's near this black hole will just get sucked into it. So if you were actually looking at a black hole, you might see things around it moving that are far away from it, like rotating around it. But anything that gets close enough to it just gets sucked in, including the light. So there's nothing to see. Which makes detecting them kind of difficult, right? The only way you can detect these black holes is to notice that things that are far away from it are rotating, and they're rotating because of it, and everything in the universe is rotating. So it's kind of hard to detect that. Or to detect somehow that space has been bent, and that's how they detected it recently with the LIGO array. So the LIGO array and the newest one, which is the MIGO array, I believe they call it. Let's look them up. And here's the here's what they actually detected. This is an artist's rendition of what they actually detected. 2 black holes that were actually rotating around each other. So 2 black holes that became very, very close to each other that eventually collided with each other. Let's watch this for a minute. We've got time.
From the dawn of our species, what we know of the universe has come from what we could see, from light. Visible light from the first stargazers, ultraviolet and infrared light from the Hubble Space Telescope, microwaves and radio waves blasting from the cores of galaxies. But there are other vibrations we can't see. 100 years ago, Albert Einstein proposed his theory of general relativity. He predicted that the acceleration of massive objects would boil the fabric of space and time, sending out gravitational waves.
So what you're actually seeing here is a representation of 2 kinds of very dense stars that are rotating around each other. This one right here is called a pulsar. It has these jets of X-rays and particles, high-energy particles that are coming out of it, and it rotates very quickly, and that's why it's called a pulsar, because it looks like it's pulsing in space, and those things can be easily seen. But over here you've got another very high-density star that has been attracted to this other star, and they're rotating around each other, and they're attracting each other still, so they're getting closer and closer and closer. What you're seeing coming away from it is the thing that we can't see. We can see these 2 stars, but we can't see what they're representing with these waves that move out from it. These waves are the space and time around these stars that actually get warped. They actually get bent. So it's like space and time means something very different than we originally thought. And that is the brilliance of Einstein. Einstein was able to say, maybe space and time are not what we thought they were. Maybe we need to think of them differently. That's really all it comes down to when it comes to the genius of Einstein. He did a lot of dumb things with his theories and a lot of dumb things with his science. But just because of that one brilliant thing, he is easily one of the smartest people who ever lived, without a doubt. Because it took so much dexterity of mind to come up with this simple idea that completely turns all of science through all of time on its head. That's what these waves represent.
The acceleration of massive objects would boil the fabric of space and time, sending out gravitational waves. Nobody had detected them until now. 1 billion years ago, in a distant galaxy, a pair of black holes circled each other. They spiraled inward and finally merged. The collision unleashed the energy of 1 billion trillion suns in a fraction of a second. That energy is still spreading outward in the form of gravitational waves, space-time distortions rippling across the universe at the speed of light. As a gravitational wave travels, it compresses space in one direction and stretches space in the other, like sound going sideways. This push and pull weakens with distance. The wave fades to a whisper, so faint that physicists long thought that gravitational waves would never be measured on Earth.
Now, the problem with measuring gravitational waves is if they're big enough for you to detect, you're probably, we don't really know what would happen to us, but we would assume that our world would be destroyed. So if one of these events happened close enough to Earth that it would be easy to detect, yeah, we'd easily detect it, but then it'd be over, you know, science would be over for the human race and Earth and everything around us. So it's ideal that these things happen very far away, both in space, and of course, if they happen far away in space, they have to happen a long time ago for us to actually see them. Because if it happens right now, 1 billion light years away, we'll never see it because it'll take 1 billion years for it to get to us, right? So it had to have happened 1 billion years ago, 1 billion light years away, right?
But in Louisiana and Washington, 2 of the most sensitive detectors ever built have been waiting and listening. Astronomy has grown ears.
It's really funny that they say they've been waiting. They turned these things on to test them, and during their test run, they detected this. They hadn't been waiting at all. They were just testing them, and they found their first black hole collision within minutes of turning these things on. And they've found so many of them since. It's just been amazing.
This is LIDAR, the Laser Interferometer Gravitational Wave Observatory. Each detector has an L-shaped antenna with arms 2.5 miles long. Inside the ends of each arm, mirrors of ultra-pure glass are isolated from the noise, heat, and vibrations of the outside world. A beam of laser light measures the separation of the mirrors. The beam is split and sent toward mirrors at the end of each arm. If the arms are precisely the same length, the returning beams cancel each other out. The LIGO's detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy is tiny, a fraction of the width of a proton, but enough to misalign the beams and light up the detector in a rhythmic pattern. On the 14th of September 2015, LIGO detected a flickering light and turned it into a sound wave.
And that's it. That's it.
A chip.
And they actually put it on a speaker so they could hear it. That's the sound. You just heard a billion-year-old collision of two black holes. Let's hear it again. Whoop.
Sure.
That's it. Oh, that's pretty cool, though. So Einstein predicted this
It was the echo of the marriage of those two black holes. A cosmic
100 years ago.
cataclysm that happened a billion years ago.
And they thought that they would have to build this and listen for maybe months or even years before they'd find one. But they're finding them all the time now. They're discovering that black holes are really common out there in the universe. So it's very interesting what we've learned in just the past couple of years with this experiment. They have another one. They just finished another pair of these. They just finished in Europe. So those are online, and they're going to have even better measurements soon. So that's kind of exciting. But this
Hearing
is
a
gravity.
gravitational wave has opened up a new kind of astronomy. For the first
So anyway, now they can start to look out at the universe in very different ways and start to discover things. This is one of the big holy grails of science, is figuring out what gravity is all about. It was one of the first things we did science with, real science, with Newton, with Galileo, with great scientists hundreds of years ago. It was the beginning of real science. It was 400 years ago with these guys. Now we're actually figuring out some of the basics of it, that gravity is a wave, that gravity behaves like a wave. If we can figure out that gravity has a particle associated with it, if somebody can discover the graviton, for example, it would change the world in ways that we can't even imagine. We're talking Star Trekian kind of proportions here. That kind of leap forward in technology, understanding, and I mean, it could be really exciting. So I'm really excited for this. I'm excited for the future, particularly for your future and your kids' future, because we're talking major things. This hasn't happened in a long time. Something major like this. So it's quite cool. And it's, anyway. Oh yes, this is actually the Nobel Prize just yesterday. Yesterday? Today! Yes. So the Nobel Prize, I didn't read this actually before, that they were up for the Nobel Prize this year along with a bunch of other people, but I think pretty much everybody thought it would be for these guys. It was given to Kip Thorne and Barry Barish of Caltech for this discovery. Oh, and also Rainier Weiss. So, that's like the 10th Nobel Prize for each of those schools. Anyway. So very, very cool. Very, very cool. I have a connection to this, albeit very tiny. This is what they call this. They call this an interferometer, and it's a very particular kind of interferometer. They showed you that the lasers go down each arm, but they don't just go down each arm. In the middle, they have what's called a Fabry-Perot chamber, and about halfway down each one of these it goes inside this chamber and it bounces back and forth millions of times, and then goes out the other end, and it lengthens the effective distance of each arm by many times, so that the arms of these are much longer than they physically are, so that the light travels much further, so that when it gets back, it actually is much more it's much more precise of an instrument. To really make this properly, these arms need to be hundreds of miles long, maybe even thousands of miles long to make it work right. But they don't have that kind of distance on Earth, so they do it with these Fabry-Perot chambers. And I did some work on Fabry-Perot chambers in the laboratory when I was a graduate student. And that's that all that work that was done back then has led to these great things. So.
The chamber, that small white house,
I'm sorry?
is that chamber that you mentioned, that white house in the middle of that?
Oh, at the two
Yeah.
arms? No, the White House in the middle of the two arms is where they send the laser out and where they get it back. The Fabry-Perot chamber is inside of the arms. It wouldn't be any separate thing. It's because all it really is mirrors. So it's just a set of mirrors that are in the middle. So it's not going to be visible from the outside. But I worked on some stuff like that. So, I have some very slight connection. Okay, so let's move back to the last section here, which is, what is our last section? Kepler's laws and satellites. So Kepler, who was around, about the same time as Newton, he came up with some laws. He was a little bit before Newton, actually. He came up with some laws about how things orbit around each other, satellites and planets and moons and things like this. And his first law was that everything moves in elliptical orbits. So everything's an ellipse. And a circle is just a particular type of an ellipse. But an ellipse is a shape that has a distance between 2 points, from 2 points to a single point on the edge, which is always the same. So this distance plus this distance is always the same length. And that's the definition of it. If it's a circle, then these 2 points are at the center, and it's always the same distance. But the interesting thing about this is his second law, which says that a planet that's going around a sun, where the sun is at one of these 2 points, which we call focuses or foci, the planet will sweep out an area that is the same. So each one of these areas, these pi wedges, is the same for the same amount of time. So when the planet gets closer, it moves faster to get across this arc length than it would when it's further. So he observed that. He observed that when objects are further away from the thing that they're orbiting from, they move slower. When they're closer, they move faster. And this is actually a geometry problem more than anything. And that's what he was doing, was geometry. But his third law was the most important, is because it comes with a formula. This formula tells us the time that it takes a planet to go around its sun or whatever it's going around, compared to the radius, or the average radius is a better way to say it. So if you have one planet going around a sun, and it takes a particular amount of time, and it has a particular radius, you can compare that to a second one's time and radius and calculate one or the other. And so that's what we learn here. So in this particular one, we have a moon that's going around the Earth in 27.3 days, and it has this average distance, r equals 3.8 times 10 to the 8. And we want to calculate the period of an artificial satellite that's going at a different distance, at a different r, above the Earth's surface. So you have to add the Earth's radius to that. But you have 2 r's and 1 t, and you're going to calculate the other t. So you rearrange it to calculate t2, and you're done. It's pretty straightforward. But that is all of chapter 6. So get started on the homework. We will come back to this to answer any questions about homework on Thursday. And hopefully be able to get started on chapter 7. Tomorrow we will have a lab. So we'll see you tomorrow. And have a good day. Have a good day.